Well, good morning. If we could, we could start the next session. So the next session is titled Demystifying Quantum and Quantum for Space and Security Systems. My name is Joel Moser. I had the distinct privilege to be the first chief scientist with the United States Space Force when it was stood up in 2019 and served in that role at the Pentagon until last year when I retired. I consider myself a technologist and a futurist, and I get to do a lot of those fun things today. I'm joined by a couple of distinguished gentlemen. Austin Hood is the president of Secured Quantum Systems U.S. Defense Company. And he brings quantum communications technology out of the lab and into the hands of our servicemen and women. He's been with SQS for only a couple of years, a company that I'm proud to be an advisor with too. But he has more than 30 plus years of operations, communications, and cybersecurity behind him. And he's working to build a paradigm-shifting quantum communications case in his current role. Also, I have Mr. COLIN DOUGHAN. COLIN is founder and CEO of GRAVATICS, focused on building space infrastructure for the DoD and commercial markets. He wants me to say, these guys build space stations and aircraft carriers for space. We'll talk about the physics of that in a minute. Prior to starting GRAVATICS, COLIN worked at Lockheed Martin for 20 years, developing large satellite constellations for the US Air Force and Space Force. But before we get into talking about that, I just could not resist as a physicist. The title of the talk is Demystifying Quantum. So I have to give a little bit of a spiel up front. This is your talk from a physicist to tell you what you need to know about quantum mechanics, quantum physics. No physics degree required. If you already know about quantum mechanics and how it works, then maybe I'm going to give you some ideas on how to explain it to your friends at parties. But I'm going to tell you, there's just a few simple concepts that you need to grasp. Anybody in this room can do quantum mechanics. You just have to be a little bit mindful of the weirdness and to put your intuition on hold for a second. So I call this my 2-bit quantum mechanics talk. First of all, because I'm going to use a quarter as my quantum analogy a lot here, you'll see. And second, because it may only be worth 25 cents, so you can tell me afterwards. So this is a spinning quarter. Your classical intuition about spinning quarters will tell you that this thing is eventually going to stop and it's going to fall down and it's going to say heads or tails. In fact, if you were able to measure the spinning of this and the balance and all the details, you could even predict whether it's going to be heads or tails when it falls down. That's our quantum intuition. I'm here to tell you that's not so in the world of quantum mechanics. So when I talk about quantum mechanics, I'm talking about the world of the very tiny, that scale of molecules and atoms and electrons and photons, very small. And it's a very sensitive area in terms of things only work in a delicate sense. They're easy to disrupt. So it's a world that we're not familiar with, and again, you have to suspend some of your intuition to understand it. So the first thing I'm going to talk to you about is a phenomenon called superposition. So in the classical world, your quarter is heads or tails. In a quantum world, so imagine this quarter is brought down into the world of quantum mechanics. It can be both heads and tails at the same time. That's called superposition. So what is that? Is that a heads or a tails? I don't know. In fact, it can display the behavior of a heads quarter and a tails quarter at the same time. But when you look at it, it's going to collapse into one or the other. It'll be a heads or a tails, and it'll be that way forevermore. That's kind of weird, and I'd like you to think about that a little bit. If I were here and I flipped a quarter and landed it on my back of my hand and covered the hand up and said, is it heads or tails? You wouldn't know, but it is either one or the other of those two. It's heads or tails, and we're ignorant of it. What I'm telling you at the quantum scale, it can be both heads and tails at the same time. You can do experiments on it. The way it propagates, the way it moves is It'll display a superposition of both states. And this applies to anything in this microscopic world that you can measure. It could be the energy of this quarter, or an electron, or the polarization of a photon, or the position. Is it here? Is it here? Is it there? All of these things can be in superposition at the same time, and that's the part that we have trouble with intuition on. So one way to think about this in the real world is think about dropping a pebble. A pebble is think of it as a particle. It's got size, it's got weight, you can measure that. It's hard, you can measure the dimensions of it. But now release it and drop it into a pond, and it turns into a wave, so to speak, sort of. A wave is a little bit different. A wave is moving in all directions at the same time in this case. It's moving everywhere. It has high points, it has low points. It has different features, and it propagates differently than a stone would propagate in water. That's the way quantum superposition kind of is. It's propagating as a wave. It's moving as a wave. And you might also have heard the concept of wave-particle duality in quantum physics. This is what they're talking about. Now imagine you look at this, you just look at this wave in the pond of water, and it snaps back into a stone. It collapses from a wave back to a particle. That's the phenomenon of wave function collapse in physics. And once it goes back to being a particle, it'll never be a wave again. Kind of hard to get your mind around, right? But let me stretch your mind a little bit further. Let's talk about another quantum physics phenomenon called entanglement. So imagine I take this quarter and I put it in a undercover in a box, and I slice it down the middle, flat way. So I have two pieces of metal, one that's got a heads on it, blank on the other side, and the other one that's got a tails on it, blank on the other side. So I'm going to call those two entangled, because now anytime you have the one coin and you see that it's heads, you know that the other coin must be tails, or vice versa, right? Because they came from the same place. Well, back to superposition. If we did that under the cover of darkness, we cut the coin in half, and I handed one of those coins to somebody, we'll call her Alice, and I handed the other coin to Bob, and say Bob goes off to Mars or to Kansas, which is even further, or Alpha Centauri, doesn't matter how far. Alice and Bob, as long as they're not looking at their coins, they can be in superposition. They can both be a head and a tail at the same time. And it's not just because Alice and Bob are ignorant about what they have. It physically obeys the properties of both. You could do experiments on these coins, and they would behave some strangely. And it's not until one of them looks at the coin. So let's say Alice turns it over, looks in her hand, and she has a head. Well, she knows automatically that Bob has a tail. Bob's magically becomes a tail because Alice is his head. And it happens instantaneously. It doesn't matter how far away they are. And if Bob now opens his hand, he'll see that tail. That's quantum entanglement. And you might imagine it might have some applications for communications, or if you sent a series of these quarters or entangled bits by Alice to Bob, you could use that as a decryption key for a cybersecurity key. That's one of the uses for this. We'll talk about it. So, you know, this is all mysterious. It's very hard to understand conceptually. It's just not our natural life. But mathematically, it's actually quite simple. Just to introduce, this is all the math you need to know to understand quantum mechanics. First of all, the quarter on the left, see the little funny symbol? It's called the bracket notation. It says H on it. So that's a quarter in the state of heads. To the right is a quarter in the state of tails. A quarter in superposition, which we'll denote by psi in the bracket notation, is just the sum of the heads and the tails. Notice there's no indication of position or velocity. It's just the sum. So the physics flows very naturally from very simple concepts like that. It's our intuition that needs the work. That's the hard part. So what good is all this? So quantum computers, we all hear about those in the news. The interesting thing about quantum computers, if you consider your quantum quarter to be a bit is usually 0 or 1 or the other. Just like a quantum quarter, a qubit can be in a superposition of the 0 and 1 state at the same time. And you can come up with gates and processes and algorithms that operate on that without collapsing it to either a 0 or a 1. If you have 2 qubits or 2 quarters, you can have 4 states, heads, 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 tails, tails, heads, tails, tails. And you can process those all simultaneously using quantum gates and this property of superposition. If you have 3, you can have 8. There are the 8 states that 3 quantum coins can be in. You notice a pattern here. Every time you add a qubit or a quarter, you double the amount of things that you're looking at once. So that's why quantum computers are so appealing. All you have to do is add another qubit and you double its capability. So imagine what would happen if you had 10, 20, 30 qubits. Amazing, right? So why don't we just do that? Why don't we just build a quantum computer that has a lot of qubits and solve the world's problems? Well, it's not a conceptual problem and it's not a quantum problem, it's an engineering problem. What do quantum computers look like? They look like this. That's actually not the computer. That's all that tubing and wiring and metal plates. That's the refrigerator that cools the bits down to close to absolute 0 and keeps them isolated. Remember how I said quantum physics is very shy and very sensitive? In order to take advantage of it, you have to isolate these things very, very quietly and carefully. That's the challenge, engineering challenge. That's why it's taking so long for quantum computers to come about. So there is one exception to that. You can actually have a quantum phenomenon at room temperature that you can hold in your hand. And to do that, I need to talk a little bit about quantum materials. This is the last concept I'm going to give you, so I don't see anybody passing out yet. So we all know that a diamond is just carbon atoms that have been compressed over time in high pressure and heat and create a crystal lattice of carbon atoms. That's a diamond. Turns out there's a defect that's possible in the crystal lattice of a diamond, where one of the carbon atoms can get replaced by a nitrogen atom. And when that happens, just to balance the chemistry, you also get a vacancy right next to it, an empty spot. And that's called a nitrogen vacancy diamond, NV diamond. And these happen in the real world. They occur in nature. In fact, if you find one, they're very rare. They sparkle more than a regular diamond. It's cool. But fortunately, we know how to make them in a laboratory. So we do make these, and the interesting part about NV diamonds is that nitrogen and vacant spot can do all this quantum physics, the superposition, the entanglement, at room temperature, because it's embedded in a crystal. You don't have to reduce it to near 0 temperature. These kind of quantum materials are very useful for quantum sensors. So beyond the scope of this talk, but using something like this, you can create a sensor that can detect very minutely changes in the Earth's gravity field or magnetic field. With that, you can render the oceans transparent and see every submarine down there. Very amazing things that can happen with quantum sensors. So my simple 2-bit talk, I've told you about superposition and entanglement and how that relates to quantum computers. I've also talked a little bit about quantum communications and quantum security. And finally, a little bit about quantum sensing. These are 3 technologies that are set to revolutionize the world. And that's what we want to talk about. So I hope that was worth 25 cents. So. So I would like to turn to my colleagues here and ask a couple of questions. And the first one, there's a lot of hype around quantum too. Everybody seems to want to throw the word quantum in front of their product. There's quantum phone cases you can buy. There's a quantum dishwasher tablet. So I used to sign officer performance reports for Space Force and Air Force officers. And I can't tell you how many times I saw Officer Stuffy made a quantum leap in new technology to acquire something. And I would always circle that and say, a quantum leap is very small. It's tiny and sensitive. So there is some hype. So I'd like to turn to first to Austin. What do you think of this hype, and how do we know when the technology is broken out of this hype cycle?
Yeah, thank you, Joel. And so when I think about this hype and a hype curve that comes through there, and from my perspective, when I want to kind of get to more what's really out there and what's available, I have to take a lot of what I get with a grain of salt. And I have a couple tools at my disposal that I use to do that. And so I've got a reference architecture so that I know what's in and out of the bounds of the realm of the possible. And also I've got a roadmap for digital transformation that helps me to identify the relevant opportunities, what's that closest alligator to the boat on that piece. But using, basically measuring those things that are being made, and research essential, right? But someone like me would get lost in the research and in the hype of the promotion of that. And so I take my measurements more so from what's being built and what's being fielded out there.
Colin, any thoughts on hyping quantum?
So most of my answers today are going to be related to how do I apply it to my products. So we are not an inherent, I don't have quantum in my name yet, although that might be a good thing we should add.
Quantum Colin, okay.
We are building large structures for the civil space industry, so think like modules for space stations, cargo vehicles for space stations. And then on the military side, Golden Dome related, we can host your space-based interceptors. We're just won a large contract to be able to provide the orbital carriers for space that can pre-position third stages in orbit, and then when needed can quickly shoot them out anywhere in systems. And I hear quantum, and I hear an exciting new maybe on the comm side. And I have to then say, if I put it on one of my vehicles, if I put that capability on one of my vehicles, what do I have to give up? And what happens if it does not work as advertised, either initially or over some extended window of time? And so largely, I'm viewing that along almost any technology I consider. Many have a lot of sizzle to them and would be exciting to be able to take advantage of. At what point does that add enough value to be worth the risk? But I think with quantum, there's the reverse risk also. In general, space moves slowly. You're almost never penalized for saying, you know what, in the interest of human safety, if I'm going to go to the ISS, in the interest of whatever it is, I got to make sure it works. And so I will take that old, rad, hard CPU rather than the latest and greatest that comes out from NVIDIA or whatever. In this case, though, the danger is, what if it moves quick enough that some of my data becomes exposed? People are gathering that data and decrypting it later. There's a whole reason why we're going to be forced to get on the quantum train. And so trying to wrestle with that right timelines can't just be that a product exists, but it also can't be that, in general, we hold off as an industry too long because it's going to leave us behind in some scary ways if we don't get on board.
You bring up an interesting point. There's sort of a fear of missing out in terms of any new technology. Everybody wants to be on board with the latest, but there's also a competitive aspect of that. And for defense, it's, does your great power competitor get this technology before we do is a big thing. For business, does my competitor bring it to market first? I'm just wondering, how much does that change the calculus of quantum technologies, whether it's computing, communications, or sensing in space? Either one of you have a thought on that?
Yes, Joel. And so I've heard others say that, when it comes to this quantum thing, specifically from a defense, national security area, there's no points for second place, right? And so we have to forge ahead and get there as quickly as possible. And our economy is no exception to that national might. And so a lot of application in that area. But I think one of the ways that we can kind of accelerate and bring those things in is to just get to know the technology, to get close to it. And so I'd be remiss if I didn't mention, from our sponsor at Space Isaac that, they have a quantum test bed pilot project. And so that's a place where companies can come to literally put their tech, their thoughts, their ambitions, and get them validated in a test environment. And not like a research and development kind of test, but like a practical day-to-day kind of application. And so just getting to know those, helps to bring down the hype a little bit, helps to get people comfortable, bridge that educational gap that you'd spent some time on us. Thank you for bringing that in so that words like superpositioning and entanglement have a little bit more meaning toward their business. And now it's, now it's starting to work toward applying that within each kind of sector. And what could it bring to you and accelerate from your business capability perspective?
The way that we'll on-ramp this tech is by first flying it on the ground, so taking advantage of some of these opportunities, introducing it into our HITL, hardware-in-the-loop lab type capabilities on the ground. That makes tons of sense. But the reality is I'm going to fly two. I'm going to fly the old tech and the new tech and try before, I guess I've already bought, but before I rely on those capabilities, because most of them do a job I already do, but can do it better. And I can't wait for the day that I can fully rely on this quantum tech across a variety of these use cases. But until then, you're going to still see me flying some of the old stuff too.
Yeah, that's great. And I'd like to follow up on that a little bit, and maybe something you said too, Austin, about, there's ground test beds testing this out. What would either one of you want to see before you did rely on a quantum technology as your primary, not just as a backup? As George Pullen said earlier about future technologies, you kind of have to discount those for the things that are available today. Any thoughts on that?
I mean, let's just take, you had mentioned earlier some of the comms-related advantages that could come from this. Some of the uniquenesses of this technology, that the very act of taking a look at it in flight, in process, while it's traveling from here to there, will identify that information, and it's no longer in superposition. I'm going to lose it. I'm going to know it, that I've been breached, and that sounds very attractive. I'll never get hacked again. What happens if that device breaks down partway in? And so I'm gonna need a long track record before I trust it, because most of this equipment goes up that has to last decades. And so anything new is going to have that same hard convincing me to not fly something that, if that does all of a sudden stop functioning, I'm loving it for 2 years and it no longer works, I'm going to revert back to old RF comms and some other methods of being able to communicate.
You remind me of something I learned from Rich Joseph, who was the chief scientist of the Department of the Air Force when I was a Space Force chief scientist. He would say, if it smells, it's if it smells, it's chemistry. If it's squishy, it's biology. If it doesn't work, it's physics. It's kind of around there. Any thoughts on what you'd like to see?
And so for me, it has to be usable and reliable. And I know in pure science, when we're doing these researches, like you showed on your picture there, it's a very controlled environment. And quantum mechanics right now, while physically bounded, is still very fragile in the way that we're developing it. And it comes down to me into the implementation of it. And so I need to have something that has a certain maturity to it. And as advances come, I'll be kind of lagging behind those advances in favor of that reliability, so that when we go to somebody or somebody wants to use this technology, we have high confidence that it's going to work and work for them, because the stakes are too high, like you said, Colin. If you're putting a couple $1 million into a satellite launch, you don't want your quantum clock to flake out on you right after it leaves the launch pad. And so, so that's where I put a lot of due diligence into looking at that reliability factor.
Yeah, yeah. So, question for both of you, but maybe start with Austin. Will quantum technologies for space or for any use become their own vertical, or will they be absorbed into, you know, other industries like aerospace and space? Any thoughts on whether we'll see a quantum industry, or will it just be a tool that's used in other products?
Yeah, and so the quantum industry is absolutely critical to securing space systems, period dot. And so I'd submit to you today that that industry, nascent, is comprised of what Colin and his company do. You know, they're highly advanced, they're highly specialized. He's alone and unafraid out there, and he's doing the things that he has to do. But it'd be nice for Colin, not to speak for you, but it'd be nice for Colin to have an industry out there of partners that specialize in areas that he doesn't have a 25th hour in the day to get to, some areas that he can't think through. And so I think it's important to build this industry up. And so will it? I think the answer is it's there. It just looks in that form. And much like artificial intelligence has grown, you know, in 2022, it was put onto the NAICS code, which is headed up by the U.S. Census Bureau and overseen by the Office of Personnel and Management, but it's the National Industry, the North American Industry Classification System. It's how we go about tagging those business efforts and putting them in bins. And it's also a way for federal agencies and others to monitor the spend of that activity. And so in 2022, we see artificial intelligence gets its own NAICS code under the R&D umbrella, but it doesn't address the business side of the house where Colin operates. And so in there is, you know, how are they going to classify and qualify that spend to formalize it as an industry when it comes through?
I'm going to use partners like Austin to help make sense of this, but I'm guessing where I'm going to see it is I'm going to have an alternative to a star tracker. Is that going to come from a star tracker company that jumps on the and puts quantum in their name and jumps on that bandwagon? I'm going to have an alternative to other sensors I would otherwise be using that give me alternatives to GPS and other things. Again, are those going to come from those incumbents or a fresh startup? I mean, history shows we see bits of both, and then who ends up winning, I think is going to be a fun adventure to watch.
Yeah, and I would point out that we have quantum technologies in operation today, had them for many years. For example, the clocks on our GPS are basically fundamentally use a quantum technology. Lasers are based on some of the same quantum technologies. So life is funny that way, right? New technologies seem mysterious, but once they creep into things, we just deal with them. I mean, we adapt things very quickly. So with that in mind, I'm just wondering, how is quantum mechanics going to help us build aircraft carriers in space?
So a lot of our products right now are in low Earth orbit, well within the reach of GPS. As we get further out, we have options. We can build new GPSs or their equivalents beyond GEO and continue to operate into an environment where there are these signals that give me precise pointing of my location. Alternatives, it's a pretty pricey way to do life, is to carry some of that capability on board. Better onboard clocks, that's a huge piece that can help, and better precise positioning beyond GEO. You can still reach the signal, but the closer you get to the moon and beyond, it becomes harder and harder to be able to use reliably. So I see that as a huge capability as we want to be able to utilize more of cislunar space. Additionally, that navigation gear of knowing precisely where I am. I mentioned some of those products are, you know, Lego brick style assembling modules in space for like space stations. That RPOC, rendezvous prox ops, making the final connection is going to be huge. And I think some of these technologies are going to be powerful there. But I think I'm also unaware of where this could go. The idea of making the ocean transparent. I mean, like how far are these sensors going to go that there's not an equivalent product that we're simply going to make better, but it's just going to change the game, and that's going to be very fun to be able to explore.
Yeah, very, very good answer. And you know, one last question maybe, and then we'll open it up for some audience questions. But Austin, so you know, Several years ago, the National Security Agency came out and said quantum key decryption, QKD, is just not the way to go. It has some problems, some fundamental problems. I'm wondering, from the perspective of a company trying to commercialize quantum communications, what's your rebuttal to that, and what's the way forward? And has that declaration slowed you down any?
The declaration hasn't slowed us down any, but I would love to have the discussion with organizations like that about what the future may have. You know, you've already mentioned that it's underpinned by physics, which is pretty hard to compete with and great to take advantage of in that area. And you know, when it comes to security applications, it's a lot about the computational risk that you're going to put out there. And not just on the technology itself, but also in the implementation. And so we're undertaking a white paper to get more thoroughly after those concerns that might be out there. But you know, when it comes to it, I see that other areas of the globe, like the EU, are a little less hesitant to adopt some of the ones that are already in place, like quantum key distribution type technologies, ones that we use too, but they're just scaling at a much higher comfort level than that. And so I think they're seeing both the pressure to need to move to an environment like that, and then also maybe they've done their homework in that area to understand what that true risk would be for them.
Yeah, thank you. Great answer. So I'd like to turn it to the audience. Anybody have any quantum mechanics lecture questions that you'd like to ask? I see one over here. Here comes the mic.
Thanks, gentlemen. I'm Clay Bosler. I support the Space Systems Command out of U.S. Space Force. I worry, I mostly work on SATCOM, and my fear for our future in SATCOM and more broadly is something I've started thinking of as spectral Armageddon, with thousands of overhead emitters, the uncoordinated, the ITU regulatory environment that was built for a pretty staid, geocentric regulation. I think we're going to have a Kessler-like syndrome, but it's going to happen in spectrum, not with birds running into each other. Given that, I hear stories that quantum will help me resolve that, move beyond that, sidestep that problem. I'd love to hear your thoughts on that and how dependent with quantum distribution are we still going to be on spectrum? How fundamental is spectrum, and how can you sidestep that with quantum? Thank you.
Yeah, Clay, thank you for the question. And so, number one, I don't think any of us up here have all the answers to all the problems up there, but I would frame my response to you in that, like I mentioned before, quantum is fragile. And so there's a lot of things that we have to take into account of for noise and the complexity that comes through there. But I like to look at it as a maturity journey. And so much like when we invented the transistor in 1947, it could easily fit in the palm of your hand. And through decades of continuous improvement, research and development, miniaturization, applications across the board, we're on track to put maybe 30 trillion of them on a chip by 2030, if I don't misquote that. And so we've gone down to having something that fit in your hand to now something that's 5 nanometers long and in place. And so I think while today it's hard to envision that time when this technology will reach its stride, I feel confident in the teams and the companies that are getting after it and the research agencies that are putting toward this to make it more usable for you in these space systems. And so it might just be a question of how, but more of a question of when could we start to see these things become meaningful and purposeful in these applications that we have.
Yeah. Where's the microphone?
How's it going? Nick Goddard, CISO at a company called GoGo. We run corporate aviation worldwide. 26 years doing DoD work over on the private sector now. And I'll tell you, one of the challenges I've run into on the commercial side is when government's usually been the primary driver for innovation when it comes to very elite systems that require the IOS constellation. You know, as an example, at GEO, very significant engineering requirements, very defined processes. We know what cold welding does. We know all the things that happen internally. Now I'm on the business risk side when it comes down to when I look at these technology companies and we talk about quantum, and I'll talk about snake oil and the amount that is out there when it comes to what quantum is, right? And so when NIST published the actual 3 algorithms, well, 3 plus if you include Falcon and a few others, on the algorithm side saying, okay, NSA certifies algorithms, but vendors build implementations, right? And they field those. So the challenge is how do we advance on the business side so we can invest in companies that are not snake oil? Well, from a technology standpoint, I evaluate things that come into my current company by looking at their track record and who's on their board. Do they have a chief scientist position? Do they have somebody that knows math, right? I got people that are selling me things that are piecemeal together from other organizations, and the risk at running quantum and turning it into a nothing burger is very real because AI is currently distracting everybody. And it really comes down to a data problem, not an AI problem. So as we feel the maturity of this organization and we want people to invest in these companies, how does folks like the Space ISAC and others come together and say, how do we actually evaluate vendors? And how do we prove that these folks are actually value added to an organization? I don't want to say like a good housekeeping seal of approval for a Better Business Bureau type of deal, but how do we build that type of framework in so that way we're not being sold magic beans?
Either you have any response to that?
Yeah, so it might be a self-correcting, self-policing kind of effort, right? If you have a good name and you're doing good work in the business, you'll be a victim of your own success. And if you're in it for the quick win and you don't have any plans for longevity, then I think it's very transparent when those companies come up with their hand open for that. And so, like I mentioned earlier, Space ISAC has that quantum test bed specifically where you can come up close and touch the components and use the things and walk away with your own validation. It's not like it's a slam dunk like, hey, I used quantum and it worked. It might be that the lesson learned is I used quantum and it didn't work for me in this case. And so that helps for me to separate the wheat from the chaff when it comes to people that can deliver and help solve the problems that you're looking for. But I imagine, much like the AI market, and it's not a poke, it's just kind of an observation that, that they are, there's folks in that crowd that are also taking the hype and people are adding on and stacking on to a phenomenon that is growing and sweeping throughout. And so same challenges apply, and I would probably suggest it's the same litmus test that you would take for an AI company that you would take for a quantum company to do your due diligence and due care as you bring those to bear.
Yeah, when I give my futurist talks, I often talk about Jim Dater, who said we often overestimate the effect of a technology in the near term and underestimate it in the far term. And that's an important concept. In quantum computing and communications falls exactly in that. We've been hearing about it for years. I started working in the quantum field 30 years ago, and it's always been there in the background, and we always have these great, this is where the hype comes from. We have these great, it's going to eliminate our problem on spectrum. It's going to solve world hunger. But in reality, it comes slower than that because there's a lot of work that happens, and so we've overestimated the effect in the present. But at some point, our human brains to extrapolate that kind of technology, which is going to grow exponentially eventually, is limited. We can't imagine some of the things that we'll do with quantum physics in the future. So we underestimate that. Just think of the internet as a model of that. Back in 1972, did we imagine all the things that the internet could do? So it's dealing with that hype, and that was back to our first question, that you're spot on. How do you separate the wheat from the chaff, and how do you know what to look at? And I think the answer to that is things like the test bed at the Space ISAC and other places like that. So I think we have time for one more quick question.
So Josh Sorensen, also from the same team, GoGo Air, doing cybersecurity and everything of the like. So my main question was actually more of just an intrigue question for a lot of the research and development that University of Singapore has been doing towards quantum satellites and quantum communications via light source. Is there anything that's kind of incorporating into a lot of what any of y'all are touching currently?
Yeah, and that's kind of without getting into a long physics description of quantum communications, one of the problems is the distance over which you can communicate, because your entangled particles or photons become, they collapse as they interact with the world. So, sometime you're thinking of hundreds or thousands of kilometers as your distance. But if you think about projecting into the vacuum of space, you can realize longer distances, especially if you can figure out how to make hops in space. So there's a natural tie between quantum communications in the space business that's yet to be realized, but there are places like Singapore and other places happening in the US to testing out these technologies of communicating using quantum mechanics through space. And we didn't talk much about it, but I think that's a fundamental area where we're going to see some development. What do you have? Okay, well, I think we're out of time, so I'd like to thank Austin and Colin for being my panelists here, and thank you very much.